Hello, friends! This is People Are Interesting with Jan K. In each episode of this show, unique individuals share stories that take us on a ride across ideas and places, featuring crocodile attacks in Indonesia, escaping war-torn Lebanon, and shark protection schemes in Mauritania. This podcast takes you where you've never been before. Enjoy and thank you for joining the club. And we're running. Thank you so much for being here. Today we're going to be talking about astrophysics. Maybe we could start by you just giving two sentences about what you do and who you are, because I don't really like introducing my guests because I usually don't do it accurately.
Oh, that's fine. So I'm Francesco. I'm a PhD student in astrophysics. I'm actually pretty much done with my PhD. I'm writing my thesis now, which is like the weirdest part of your PhD, where you have to sum up 3 years of your life and what's been your work into one piece of text. So it's the moment where you're most critical about your work and also know most about it. It's kind of an interesting place to be. So I work on planet formation. So I try to understand how planetary systems came to be, right? Which is actually surprisingly something we don't understand particularly well yet. We don't know very much about how Earth or the rest of the planets in our solar system ended up looking the way they do, and that's what that's what we're working to understand.
Got it. So that actually made me think about something I find interesting. What areas of astrophysics would you say we have good grasp on, and which are yes, we know nothing about that?
It's hard to say because a lot of things in astrophysics are people have been fascinated by the stars for a long time, so we've been studying a lot of things for a long time, and there's a lot of fields where we have done a lot of study and we're convinced we understand them very well, until we go again in more depth. We study them again and we realize that we don't actually really understand them particularly well. For example, everyone was pretty convinced we understood the structure of other planets quite well. And then every time we send a probe to those planets within our own solar system, we realize that we're actually quite wrong. For example, most recently, there's been a mission to Jupiter called Juno. And that mission has been studying a lot of things about Jupiter, including what are called its gravitational moments, which is how the gravitational field of the planet looks from different angles, different. If you try to figure out the shape of its gravitational field, let's say, and from that people who know what they're doing, which is not me. This is well outside my field, but they can figure out how the planet is made up on the inside. And it turns out that we were expecting Jupiter to have a small compact core made of heavy stuff and then a bunch of gas around it. And it turns out that's actually not what it seems to look like. It seems to be it seems to be a much larger core, a lot more solid materials than we expected. But at the same time, it's diffuse. So there isn't a sharp transition between solid stuff and the volatiles around, the gas around it. It's rather it's a lot of solid stuff dissolved in the gases around it. So it's this diffuse core.
Got it.
So it's there isn't a sharp transition between gassy bit or atmosphere of Jupiter and core of Jupiter, but rather this gradient, which is quite interesting.
Can I ask you? So, is this a graphic picture of the gravity, pattern of a planet? How can you see it? Because when there was this big moment when they showed a photograph of a black hole, right? And it was only a rim of it or something like that. Because I don't know if you know the case I'm referring to.
Yes, I know exactly. I can't. The M49.
Uh-huh.
I think that's the name of the black hole. I can't remember.
M25 motorway around London. Is that it?
Yes. Well, actually, that's also a black hole, right? You can never get out of it.
Yeah.
Once you cross it. So, yeah, but that's the thing, right? Like at least from the physics that we know, you can't see past the event horizon. That's the point where light just falls into a black hole. There's no
really?
way.
That's the term for it.
Yeah, it's called event horizon because physics stopped working at that point.
Oh, wow.
So of course we can't see past it because physics doesn't really work there, or at least the physics we know.
Right.
And light cannot escape. So all we can see is the way that things move around it, and what we observed actually the rim of the black hole, if you want to call it that, is it's accretion disk. It's the gas that orbits it, and the thing is like it orbits it extremely fast. And when things orbit something, like when gases and like non-solid things orbit, they tend to shear. Right? They don't orbit as like a solid object. Like it's not everything is moving at the same speed. The things that are closer in are moving faster, which means that you get like a lot of friction as you move out because like at every point you are, something next to you is moving just slightly slower or slightly faster. So it's a lot of friction, and that friction heats up the gas to like unimaginable temperatures. Like we're talking millions of degrees, and so it's like super bright in like X-rays and well, also radio waves and stuff. And that's what we detected. Like we detected a bunch of like light from the accretion disk of the black hole.
Okay. And when it comes to formation of planets, do we know how Earth was formed? How good is our understanding of this topic?
Well, it's a hard question because our understanding is relatively good in a sense, because we know that at some point there was a disk of gas and dust around the sun, and then the dust in that disk collected and formed a planet. So on a surface level, our understanding is very good. But how these things actually happen, we don't really understand. And the more we look into it, the more we just end up with questions, really. Because I mean, we don't really have a lot of like concrete observations about what is happening in these disks. Only recently we've managed to like really get good observations of the disks themselves.
But by that you mean that we looked into space and we saw some, let's say, disks that could
right. Okay, sorry. I'm skipping many steps here because it's like this is so. When stars form, you form a star by like collapsing a cloud of gas, right? Gas and dust and stuff, and just collapse it down to form a star. But most of the stuff doesn't immediately fall onto the star. Well, most of the stuff immediately forms the star, but then you're left with a lot of mass that's just orbiting the star.
Got it.
And it's trying to like accrete into the star gradually, like fall onto the star. This mass of stuff around the star forms a disk. And it's within that disk that we form planets.
Okay.
That disk is made up of both gas and dust. And it's actually very hard to get the dust in that disk to collect and form planetary cores. So if the disk is like super, super massive, like we're talking very massive stars, then it's possible for the gas itself in the disk to be like heavy enough to collapse again into another object. If it collapses, if it's like a huge amount of mass, it can collapse into like a small other star.
Got it.
If it's not enough, it can collapse into what is called a brown dwarf, which is like a failed star.
Oh, really?
Yeah, it's just not quite massive enough to like start up the nuclear fusion in the core or like sustain nuclear fusion in the core. Otherwise, by this process, you can also form very large gas giant planets, things like Jupiter, but also even larger. But of course, by this process, we cannot form terrestrial planets, or even any of the planets we really observe in our solar system. This is a slightly controversial statement, because there has been some studies that claim that you can actually form planets this way, but the jury is very much still out. I'm very skeptical of this claim.
Okay.
That's an aside. we don't understand the mechanism by which we can collect the dust into like planetary embryos, what we call into like the seeds of planets. It's just a surprisingly hard problem. I think that's the.
So, just to clarify my understanding, how those massive disks kind of come to being from which stars are first formed? Because I understand that you will never have a planet unless you have the star.
Right. Yeah. Exactly.
Okay.
You won't. You first. So you have areas in galaxies which are much richer in gas than the rest of the galaxy, and usually called these like star forming regions or like. And in these regions, just like you will have like old generations of stars which explode in like supernova and stuff like that, and the shocks can sort of like cause enough like change of density, for example, in the gas for it to start collapsing under gravity.
Okay. Listeners, we are outdoors. We're enjoying outdoors on a cold May day in London. So, the water birds, you're graced with water bird sounds as well. Not only astrophysics.
Yes.
You don't have to thank us.
Yeah. So, what was I saying?
You were saying that there are those areas in the space.
Star-forming regions.
Yes.
Yeah, there's just a lot of gas there, and whenever you have like a bit of a denser region, it tends to collapse under gravity. It's just gravity takes over and collapses it, and you form a star. And then the material that is like got too much like angular momentum to just fall onto the star ends up forming a disk.
Got it.
So you just end up with like a star and like a disk of stuff orbiting around it. And then it's within that disk that you can form planets or not form planets as well. I mean, we don't know that every star has planets, and we don't know, well, probably not every star has planets.
Oh yeah, but every planet needs to have a star, or not even that.
Well, you probably need. Our understanding is that you really need a star to form a planet, but that doesn't mean that every planet in space is orbiting a star. There's plenty of there's plenty of planets, most likely.
They're flying away.
Yes.
God bless them.
Yeah, there's probably plenty of planets in space just floating around.
But are they then called an asteroid, or what's the distinction between an asteroid and a planet?
Usually, I think they're usually called rogue planets.
Rogue planets?
Yes.
Oh.
Because they don't have a pair. They aren't orbiting their parent star anymore. This usually happens because like the early formation of planets, of planetary systems, is like a very violent process, most likely. And interactions between planets and their stars and stuff can throw the planets out into space.
Oh wow, okay.
So like if you're a small planet in an orbit close to a massive planet, think Jupiter or something, if you get too close, you can just get like thrown out of your planetary system. You get one kick and your orbit changes, you get another kick and your orbit changes further, and eventually your orbit changes enough that you're no longer bound to the star, and you're free floating in space. So, there's a good chance that a lot of objects in our solar system met this fate. Our solar system is pretty busy. There's a lot of large planets around, probably enough to cast a few big rocks into space.
Is our solar system in any way unique based on what we observe in the space?
That's a hard question. So, quite recently, actually, this may seem like a weird tangent, but you're going to have to bear with me. So, quite recently, a Nobel Prize was awarded for the first discovery of exoplanets. The discovery happened in 1992. A certain guy, Didier Queloz, he works in Cambridge now, actually. He's a very interesting guy. But so he made the first real observation of an exoplanet. And this exoplanet was like a Jupiter-sized planet orbiting a period of about 1 day, or less than a day even, around its host star. At that point,
Wait, sorry, let me just ask you, what is an exoplanet?
It's a planet. Oh, sorry, it's a planet that's not within our solar system,
Oh,
right?
okay.
It's a planet around another star.
Okay.
So that's that's a bit of weird jargon that I assume that people know, but for no reason. So an exoplanet is just a catch-all term for any planet that's not a planet within our solar system.
Got it.
And so we observed this. We observed this exoplanet, and it was orbiting really close to its parent star, and that's just because of the way we were observing. Right, we were looking for planets by seeing how the stars move under the gravity of the planet, right? So the planet orbits the star and sort of tugs the star along with it a tiny bit, so it wobbles. And of course, it's always easier to observe very big things very close because they cause the biggest, most high-frequency wobble. That's like just you look at the star and you're like, oh, that star's wobbling. That's easy to spot.
Yeah.
So what we ended up with was a very big, like a very big observation bias, right? We tended to observe things that were big and close. So for a long time, if you asked me, is our solar system typical, I would have said no, because we don't have a big close by thing. As our observation methods changed and we started using this method called occultation method, which is like you see when a planet crosses in front of the star, and also our radial velocity, which is the wobble method, got more accurate. We started observing other things that were both further away and less massive. At which point, we started seeing planetary systems with a lot of larger than Earth-size close-by planets that often cross in front of the star. And we started realizing that, in fact, massive Jupiter-sized planets orbiting close to their parent star, not very common in actuality. They're just very easy to observe. So our observations are polluted, let's say. They're not true. They don't truly represent the statistics because, of course, it's more easy to observe a specific thing, so we tend to observe much more of that thing. So it's hard to say, even today, right, it's hard to say if our planetary system is characteristic of a planetary system in space because our observations tend to favor planetary systems that are drastically different. So things that look like our planetary system, we haven't observed many of. But at the same time, that's really not surprising because if you work backwards, right, if you assume that we were aliens on our closest planetary system, Proxima Centauri,
right,
and we look towards Earth, would we be able to observe Earth with our current technology? And the answer to that is no. We wouldn't. We wouldn't know that Earth was there. We'd be able to see Jupiter. If we were lucky, we might be able to see the ice giants. That's a bit trickier because their orbit is so infrequent that we'd need to get lucky to spot them.
Wait, when you say ice giants, you mean Uranus?
Uranus and Neptune.
Okay. And they are ice giants?
Just because they're big and cold.
Oh, but as in they are... the temperature there is low, or they're made of ice?
The temperature is low, and they are generally we talk about them as being rich in ices because the temperature is low and they have a lot of volatiles that are frozen. So a lot of they have a lot of water, a lot of methane.
Oh, really?
And all of these things freeze out in these.
Oh.
But for that matter, also Jupiter has a lot of water. Water is very common in space.
Because recently I think they were quite excited, correct me if I'm wrong, that they discovered, or they are very likely to discover water on Europa, on this moon of Jupiter or Saturn, or am I mixing
Jupiter.
it up?
Yes. Look, as far as I know, Europa probably has a lot of water. Europe is probably covered in water.
Right.
And that in and of itself isn't necessarily surprising, because if you think about it, what's the most common atom in space? It's hydrogen.
Okay.
The second is helium, but helium doesn't do much of anything.
It makes your voice be very thin if you breathe it, right?
Yes, yes, it does. So does hydrogen. Actually. It's something.
Oh, really?
It's about the sound speed, the speed of sound through hydrogen and helium, which is faster.
Versus air.
Versus air. Yes.
Got
so
it.
if you breathe some very heavy gases.
Yeah.
I can't remember the name of the gases. It's very very dense gas. It makes your voice really low instead of
Like
really
argon or something like that?
I think argon is heavier than air, but only slightly.
Okay.
No, it's like some sulfur compound. It's very, very heavy.
Got it.
It's like you can float like a tinfoil boat on it, kind of thing.
Oh, really?
Yeah. It's really, really cool.
Well, have you seen it in the lab? How does it look like? Is it transparent?
It's transparent.
But
I think it's odorless as well. Yeah, so you can fill a tank up with it, and like if you put a boat on it, like a tinfoil boat, it will float. Just because like the air.
That's hilarious.
Yeah.
Are there any like commercial application for those kind of gases?
There are actually, but they're also really, really polluting. Like they're, if you think like the CFCs, the stuff that used to be used in fridges and stuff, it's like bad for the ozone layer. This stuff is like uber bad for the ozone.
Yeah,
I think it used to be used in like the AirPods of Nike Air shoes.
Really?
Because being much heavier, it takes much longer to like move through the plastic, like diffuse through the plastic, so that they didn't lose pressure as fast. Something like that. Also, it bounces better for some statistical physics reasons.
Got it.
It bounces much better than air. So like, if you fill something up with it. But yeah. So going back to the previous thing I was saying, hydrogen, most common thing. Oxygen is like pretty much like the third most common atom in space. So by extension, the most common molecule, like the most common combination after H2, which is like just two hydrogens, is H2O.
Right.
You take like pretty much the two most common things, combine them together, you get water. So it's a logical expectation that water will be quite common in space. And it is. There's a lot of water in space. And you should probably pause because we're gonna.
Oh yeah.
Yeah, we're gonna get wet.
We were talking about water on Europa.
Ironically, right?
Yeah, exactly. What an irony. So we were saying that the water is quite common in universe or in space, however you want to say it, because I think you were getting into the elemental chart and why.
Oh yeah, like that's the thing, right? I think it's effectively one of the most common molecules because it's easy to form and there's a lot of the stuff that makes it up, right? That's the thing. There is relatively a lot of oxygen and definitely a lot of hydrogen in space, so you expect water to be quite common. In fact, it is. If we look at comets, for example, there's plenty of water, and if we look at Earth, there's plenty of water. It's just, and also if we look at the exoplanets, there's strong evidence that a lot of them are what we call ocean worlds. They're sort of like Earth, except they're covered in like many kilometer deep oceans.
Really?
Yeah, just because water is quite abundant in space. There's a lot of it around. So if you're making planets, it's an abundant material, and depending on how you end up making the planets, sometimes you'll end up with a lot of water on them. And sort of the same thing goes for Europa. It formed far away from the sun, so the water isn't all vaporized. Formed around Jupiter, which is far away from the sun, and there's a lot of water at that distance from the sun because there's a lot of ice. And so, we expect there to be a lot of water in many different forms out around those further away orbits. But the problem, of course, is the water liquid? Because, we're pretty sure there's a lot of water on Europa, but if there's just a bunch of ice, that's not very useful if you're looking for life, right? That's why liquid water is exciting, because life, as we understand it, likes liquid water to form, to come about. And Europa might be a good place because it's heated from the inside.
What do you mean?
Well, that's the thing, right? So there isn't enough sunlight out at Europa to melt the ice or to like make the temperature on the surface high enough for there to be liquid water. In theory, there isn't really enough at Earth's orbit either. But because we have an atmosphere that keeps us warm...
It's raining.
Yes, I just felt that.
You felt that too, right? Okay, let's see what happens.
Yeah. Put the lid as closed as you can, and
okay.
Let's see how this goes.
I already know it's not going to go well. Damn it.
It's making fun of us.
Yeah. Water is quite common on Europa, and it's a prerequisite for life as we know it.
Yeah. Like, you need water to get, like, Earth-like life, right? We don't know. Like, life is possibly, right, more resistant and like more resistant than we think. We always assume that it's going to look like Earth. There's no reason for us to believe that.
Are there other theories that that life might be exist in different, how would you call it, like environments?
Yeah, I mean, I don't know, right? Like, this is a big question. This is like one of those like essential, fundamental questions. It's like, oh, does life need to look like life on Earth? That's definitely above my pay grade to even try to answer. That's a big. I think it's even a big question in biology, right? Like, what do you need to have life? But yeah, like, if you have the same conditions as Earth, then it might be fair to assume that it's possible to have life. And Europa might have similar conditions in some ways, because of the way it orbits Jupiter, and Jupiter being much more massive than Earth is. The tides on Europa are quite dramatic.
Oh, really?
Likely. Yeah. There's enough to keep the enough. I think. Hopefully, enough to keep the core of the planet hot, or the core of the moon hot. Hot enough to have liquid water, right? So instead of being heated by the sun, you're heated by the tides. So you're heated from the middle instead of from the outside, which is interesting, right? And there's a lot of theories of how life formed on Earth, and one of those theories is that it formed around like geothermal vents in the ocean. So I guess that's kind of, if that's how life formed on Earth, and those are the conditions we have on Europa, then maybe Europa is a pretty good place to look for life. And I mean, I think that's sort of been the consensus in like planetary sciences for a while now. Like, I know in the media, like, life on Mars is like a big topic, but in the scientific community, it's all about life on like Europa or Enceladus. Like, the moons around massive planets are very promising for life, for the search for life.
Is it anything particular about the moons around big planets?
It's nothing in particular specifically about the moons, right? But it's just that because of this tidal heating, you need a bigger planet to like drive a good amount of tidal heating. And so if you're looking for life on a moon, either it has to be close to the sun, but then it's hard to keep an atmosphere because moons are quite small, so like the atmospheres blow away very quickly. So, if you're looking for close to the sun, you need a planet. So like Earth or like Mars or like Venus, and I'll probably get to that in a sec, because that's another interesting recent development. But if you're looking for life further away, moons are very good because, again, they're heated from tides, so you don't need to worry about holding onto an atmosphere so much. And also they're further from the sun, so it's harder for the atmosphere to get blown away. So, yeah, you're more likely to find things that are possibly hospitable to life, maybe. But, again, we don't really know what life outside of Earth looks like. We have a sample of one. So it's hard to say, like, this is where we expect life. In fact, quite recently, in our search for things that are potentially biomarkers, people have come up with this biomarker called phosphine. It's...
Sorry, what is a biomarker?
Oh, right, yes, sorry. Sometimes I use terms that, like, we take as a given, but aren't. Biomarker is like a molecule that you can observe, in like an atmosphere of an exoplanet or of a planet, and be pretty certain that it's caused by life. There's specific molecules or specific combinations of molecules that don't really form in nature unless you have biological processes taking place. This molecule phosphine can form, it can be formed by like volcanoes in small amounts, but also, there's a lot of it in Jupiter, for example, because there's very high pressure. But as soon as the pressures get lower, it's very hard to form, and it breaks down very quickly as well. So you need like a considerable source of it to be able to detect it. yeah, astrophysicists astronomers really were looking at planets in our solar system, and they saw phosphine on Venus. You know, the planet that is renowned for being very inhospitable to life. Is that at the surface it's the hottest planet in our solar system.
What's the potential explanation for that?
Well, the people that observed it are very adamant that there is no known explanation other than life.
Really?
Yeah, it's actually kind of interesting. I mean, we still don't know if the observation, how robust the observation is. There's been a lot of back and forth in the scientific community about how much we can trust this observation, which actually I think is kind of worrying. The fact that, like, Venus is like pretty much the closest planet to us. Venus and Mars are the closest planets to us, and even then we're having trouble being sure about whether our observation of like a molecule in the atmosphere is reliable, which is kind of scary for the prospect of, like, if we're going to observe anything in exoplanets, how are we going to trust those observations that we can't trust observations of something on Venus? But anyway, that's sort of an aside. Yeah, and the only explanation, if these observations are to be trusted, which they probably are to some extent, the only explanation is either there is life on Venus somehow, and there's been a few potential ways in which that could happen, or there's other ways to form phosphine that we aren't aware of, and that's chemically interesting. Chemists have like missed something important or something. On the life side, what the explanation that was brought forward is that there's some kind of like bacterial life or something, and phosphine, in at least from our understanding, only forms in anaerobic life, so like life that goes on without oxygen. There's a lot of it at the South Pole, for example, from from penguins' intestines. So it's like we get a lot of phosphine from some bacteria that live in the intestines of penguins, so we can detect it in like their poop.
Interesting.
Yeah. And the idea is that there's like bacteria and like bacterial spores that float on the clouds of Venus, where the temperature isn't too hot and it isn't too acidic, because the environment on Venus is ridiculous. It's like 500 degrees centigrade, and there's like constant sulfuric acid rain. That's not exactly the place you'd want to live.
Wow.
So yeah.
I actually, on this point, I read the other day that there quite soon there's gonna be a bunch of new telescopes, like a new generation of telescopes, and the purpose behind them will be to look for the biomarkers that you've mentioned on exoplanets.
Yeah, hopefully. I mean, there's a lot of new exciting stuff that's seeing first light, which is the term that we use, I guess, for opening a telescope. Like, the first light is when you. So if you look on Wikipedia, and they will have date of first light, which is like the projected opening date of the telescope, the projected first observation.
Oh yeah.
There's a few different kinds of exciting new telescopes. So there's James Webb Space Telescope, which is, I guess, a big deal. It's been in planning for ages. It's been meant to replace Hubble Space Telescope for decades now. It's been very delayed. I think NASA was maybe a bit too ambitious with what they planned. Like, all the technology didn't exist when they decided to make it. It's like one of those big decadal projects. Ended up being delayed by a decade, I think, more than a decade maybe. And it's an infrared telescope, so it's going to be observing at lower wavelengths, which is very good for a lot of biomarkers. Like a lot of these molecules have characteristic emissions and absorptions in the infrared range, and like being able to observe in that infrared range is very important. But of course, it presents a huge amount of challenges. You have to like thermally isolate the telescope. This is really, really difficult, and that's why James Webb has been so delayed, because it's such a challenging project. And then we have a bunch of Earth-based telescopes that are super exciting. I mean, there's the GMT, I think it's called, which is the GMT or TMT. Yeah, TMT, 30-meter telescope. Supposed to be built on Mauna Kea. That's a whole political issue. I don't want to go on either side of that issue.
Wait, what's the background?
It's because it's indigenous lands.
Oh,
and,
I see.
It's a big issue.
Where is it?
In Hawaii.
Okay.
On Mauna Kea, which is the highest mountain in Hawaii.
There's no light pollution there, right?
No light pollution. It's quite high, so the seeing is reasonably good. Like the quality of the quality of observations would be reasonably good because there's less weather in the way.
Yeah.
And also it's in the northern hemisphere, which is a big deal because we have very few good telescopes in the northern hemisphere.
What's the difference? What's the, in terms of observation, advantage of, or what are the advantages and disadvantages of telescopes placed in space, like the Hubble telescopes, versus the ones on the ground?
The big advantage of something in space is that you have no atmosphere to look through. Atmosphere is difficult, partly because, if you're looking for things emitted, like absorption lines from gases and stuff like that, you first need to account for the ones in the atmosphere, which is, our atmosphere has a bunch of biomarkers, because,
right,
and it's hard to distinguish what is from what is caused by Earth and what's caused by our atmosphere and what is actually coming from outside, and then it's hard to account for the oscillations in the atmosphere, from the pollution in the observations from light being refracted within the atmosphere. Yeah. That's very difficult. There is this method called adaptive optics where you bend a mirror to account for them, and you have laser beams in space, and in space you shoot laser beams through the atmosphere to get an idea of the turbulence, and then you try to account for it. It's a really complex field. I don't really understand how it works. It kind of blows my mind, but with adaptive optics you can get really crisp images through the atmosphere, and that's all large telescopes now have to use adaptive optics, because otherwise you're very limited in the quality of observations that you can make. So the TMT in Hawaii would be one of these super large telescopes. But even more exciting to me, at least, is the ELT or EELT, which is being built in Chile. In the high Atacama Desert. It's at 5,000 meters altitude, amazing quality of seeing, and it's in a desert as well. It's
dry
the
air.
Highest altitude desert on Earth. It's amazing, super dry air, never rains. It has, I think the Atacama Desert hasn't seen a drop of rain in 5,000 years or something ridiculous
like wow.
that. Yeah,
That's
it's insane. Honestly, out of places I want to go, I
That's
in my
out
lifetime, I'd love to see the Atacama Desert.
Really?
It's one of those one of my colleagues, she left science, she left academia now. She's a postdoc, and she worked on ALMA, which is the large millimeter array in the Atacama Desert in Chile.
It's another telescope.
It's another telescope.
Okay.
It's a kind of different kind of telescope because it's made up of a bunch of antennas, and they see in in the far infrared, so very low frequency stuff, and even sort of into the microwave range, that kind of frequencies. And it's a super high, super cool telescope in many ways. And that's also up in the Atacama Desert, and she's been up there. She is from Chile as well. So, very, very cool place. I really want to go, but and the telescope opening there, the ELT, is will be the largest telescope on Earth. Well, the largest telescope that we've ever built. Period. Optical telescope, highest resolution out of anything, and that would really change the way we observe protoplanetary disks, the disks around young stars. There's a lot of time cut out for the observations of forming stars, and of course, forming planets by extension. And I think that will really change our field because we're very limited now.
That actually perfectly leads to my question. What are each of those telescopes purpose-built for specific tasks, or they are very broad in what they can do? How do you kind of approach?
Well, this is each community in astrophysics, I think, would love to have a telescope built to their specifications, but realistically, that's not really ever going to happen in many ways. There's tools that have been built for specific purposes, but these tend to be quite a bit smaller. Like, for example, the Kepler Space Telescope, which is really the tool that we've used to observe the largest amount of exoplanets, which is it's a telescope that just looks at stars and looks at their brightness and tries to observe planets crossing in front of them. It was up in space for a very long time. It observed like thousands of exoplanets, and that was built for exoplanet hunting, effectively. Like that was its purpose. It also got used for other things, like observing like stars and like the brightness patterns on stars and stuff. But it was purpose built. But if you want something like super super high tech, like James Webb Space Telescope or like the ELT on Earth, you end up having huge collaborations, like a huge, not even collaboration isn't the right word. Yeah, like it's international collaborations with like space agencies and like telescope agencies, and like you will have a European Space Agency and the European Southern Observatory, all like getting together to pull the funding together. And when you do something like that, you want to make the most of it. So you try to build something as general purpose as possible. So, the ELT will not just be observing forming stars. It will be observing a bunch of stuff. It will be looking for life in space. It will be doing like cosmological observations for cosmologists. So it's going to be doing like a broader range of stuff.
Got it.
The same goes for like this other telescope that's being built in South Africa. It's called the SKA, Square Kilometer Array. That's what it stands for. It's a radio telescope that's being built in South Africa, and it aims to produce some of the highest quality cosmological observations that we ever had, and also it aims to look for like biomarkers and stuff like that in protoplanetary disks. And these huge projects are only possible through collaborating with people in different fields, because, I wish that governments would spend more money on science and less money on frugal stuff. But even then, honestly, I think there are higher priority things than astrophysics. If I were to allocate funds, yeah, of course I'd want funds to be allocated to astrophysics just because it's interesting, like science is science, and I think it's worth pursuing kind of regardless. But there's also like a lot of aspects of science which directly help people's lives, like there's a lot to be studied in medicine still, and like cancer research and stuff, and of course that kind of stuff has to get priority. And then a lot of governments see it that like a lot of like military stuff gets priority as well. And
you want that nukes ready.
You
want that nukes ready.
What can I say? I mean, it's your podcast. I don't want to get political. So
you can get political. I don't mind.
No, I mean, I don't think that's the best way to spend money, personally. I understand that like we've gotten to this point now, and sort of like, yeah, keeping peace is now somehow about like everyone being scared of each other, but I think that's a very unstable kind of peace. There's like very far to fall.
Yeah, because we're fucking apes,
Yeah.
We're like sticks and stones. Just we have better weapons now, but essentially we're like the same like animal instincts are driving us: fear, intimidation, threat. Like we're still like operating very much on that level, and so it like makes perfect sense that people like have nukes, because like we still like speak language of like power, I think.
Yeah.
As as humanity goes.
Yeah, I like to believe that maybe we've sort of we're better than that, but I think I always get proved wrong. So that's,
You think so?
yeah.
Actually, one more thing that I find quite interesting is when it comes to how the planets and stars are created, are there certain patterns, or is there just one universal way in which it works?
Well, it's hard to say, right? Because we don't really know how planets are created. So that's a big... we don't know how planets form. So it's hard to say, you know, like this kind of planet forms this way, because we don't know. We understand star formation a bit better. But even then, right, like we know material collapses and forms stars. Depending on how much material you've got around, you're going to get different size stars. Past that, I mean, yeah, that's what we know. We don't know what goes on though during the formation of a star to very high precision. But of course, I'm not a stellar physicist, so I'm not really that familiar with how well we understand the processes that take place during star formation. I am much more interested with the period of time after the stars have already formed. And I mean, actually, sorry, this sounds really strange maybe, and like to people who aren't in science, you know, like there isn't such a clear distinction between planet formation and star formation. You know, like the fields sound so similar, and yet if for a lot of people in science, there's, you know, we work on like a specific niche, and like, you know, sometimes it's like fun to do like vanity projects outside of that niche, but like realistically you end up being like hyper specialized on like something that, you know, you and another 100 people around the world care about. And like you know, it's even worse than what I'm depicting here, right? It's not just like, oh, I care about planet formation or star formation. Like, no, like my work consists of like writing simulation, like computer simulations to study the way dust moves in protoplanetary disks. It's extremely specific, and in practice, that's sort of like, at this point, it's sort of the only way to make progress, because like we don't have enough time really to like have like a huge breadth of, like a huge width of knowledge that's also very deep, just because I mean, there's people who do, but those people are rare to find, and like they're like the wise old people in academia who've had like enough time to like dive in depth in like a lot of different fields and sort of connect them together. Yeah, I mean.
And in terms of scientific community, your, let's say, scientific circle, what are your thoughts on life outside of Earth? For example, recently there was this talk about this really flat object that crossed, you know, our solar system. Yeah. What do you think about that? What do people that, you know, you talk to, what do they think about that? And generally speaking, so I would say that this is maybe just a symptom of a bigger, you know, issue, which is like life outside Earth. What do you think about that?
So, I mean, there's all sorts of... this is purely speculation, right? We don't scientifically know anything. We don't have any observations or any like hard data to go on. My personal opinion is that, you know, I'm very much I'm very much a believer in like some kind of like statistics, I guess. So, you know, if we are here now, most likely we are not that special, right? There's probably other civilizations more or less at our level of development elsewhere in the universe. Probably not very close, because otherwise we would have kind of spotted it. We are kind of easy to spot now, I think. If you know what you're looking for, we are relatively easy to spot.
How far do you think a civilization like us would have to be from us for us not to be able to spot them?
Even within our galaxy, we've only been emitting like a huge amount of like radio waves and stuff for less than 100 years. We've been polluting our atmosphere for more than that. So, if you're good at like looking at if you have like a civilization a bit more advanced than our own with like very good telescopes and stuff like that, you could probably look at Earth from quite far away and be like, oh yeah, that planet is polluted. But we haven't been polluting for that long. You could guess that Earth has life on it probably if you could observe it and you could observe its atmosphere. Like the combination of gases that are in our atmosphere are quite indicative of life. It's an atmosphere full of oxygen is, I wouldn't say impossible, but is very unlikely if you don't have life. An atmosphere full of oxygen with some methane and like a bunch of like trace biomarker elements, that's bordering on impossible without life. So that's the big thing, right? Like if you're an alien civilization, you look at Earth, you're like, there's probably life there. If you're advanced enough and you're looking at the right time, because again, as I said, we've only been producing radio waves and like signs of civilization for a short time. If you're at the right place at the right time, you could look at Earth and be like, yeah, there's probably some kind of intelligent life there. They're emitting radio waves in a way that we wouldn't really expect randomly from a planet, and they've polluted their atmosphere. So, if I were an alien civilization looking at Earth, I'd be like, yeah, they're developed enough to know, to be industrialized, but not developed enough to do something about the fact that they're destroying their own ecosystem, right?
Right.
It's like, so we're at that weird limbo where if we don't develop fast enough, we're probably going to wipe ourselves out, and that's probably an issue, right? Like it's possible that that intelligent life or like civilization is self-annihilating. So civilization happens maybe often in the universe, but is very transient. Like it appears and then disappears within what's relatively a flash within like the lifetime of the planet. Like civilization wipes itself out long before it manages to really make a mark, to really like be easily detectable. So that's why we haven't detected civilizations yet, just because they're so unstable.
Okay, fair.
I don't know. Definitely, in my opinion, Oumuamua is interesting, extremely interesting.
Oh, really?
But not a sign of extraterrestrial life. I mean, I know there's been like a lot of theories about it being like a broken light sail, and I mean,
why? Do you understand what's the argument for it being a light sail?
Because it had a weird acceleration pattern when it was leaving the solar system. But realistically, that's just a bad understanding on our side of the shape it was. I don't think it's that interesting. Like, I don't think the spurious acceleration was that exciting. It probably had some more gas in it than we thought it had, and like that boiling off due to the sun accelerated it or something like that. If it was a light sail, it was a very bad light sail. So I really don't think an intelligent civilization that's sending, things into deep space is building things that we can look at with our engineering and be like, that's pretty poor engineering.
Oh yeah.
It's an interesting object also because, it's really the first object that we've observed that we know came from outside our solar system. And realistically, there's probably a lot of things that come from outside our solar system, because just within the same year, we also observed another comet. I can't remember the name to save my life now. Borisov? Yes, Borisov, I think it was called. And that was also from outside our solar system. So actually, most likely, things cross our solar system from deep space quite often. There's a bunch of chunks of garbage, like remnants of planet formation have been thrown outside their own system, just floating around in space, and they cross our solar system quite often, and we just didn't have the technology to observe them and to spot them, and we didn't have enough telescopes just constantly pointing at the sky to realize this was happening. Now we do, and we realize that there's a lot of random stuff in space, and that, like, the frequency with which they cross can tell us something very important about how planets form, and like how much material gets like thrown out of systems when they form. It can tell us many things, and it can also tell us about, like, you know, the composition of like forming planetary systems. But I wouldn't say it's a sign of intelligence.
Got it.
I think that's my.
So would you say that the recent discovery on Venus should be is way, because I feel like the Oumuamua, or however it's called, it sounds like a like an African tribe or something, rather than a name of an extraterrestrial thing. But what I'm aiming at,
it's named after I think it's actually a native Hawaiian name.
Oh, really?
I'm pretty sure. Yeah, I could swear it is, because it's it means something like traveler or something.
Ah, okay. So do you think the Venus thing, that's more, let's say, promising in terms of looking for extraterrestrial life than this object?
Well, I think Oumuamua was an interesting snippet into what's going on outside our solar system, but it was just that. We observed once, it slid past our solar system extremely fast. We managed to get a few observations of it, and that's it. It's gone now. We can't see it anymore. We can barely see it anymore. I don't think we can see it at all anymore, to be honest, even
Fair.
with the highest resolution telescopes. No, for sure we can't. But the potential life on Venus thing, that's, for search for life, that's interesting. There's a lot of talk now, I think, of organizing a mission to Venus, because we have
of that?
Yeah, I mean, that's pretty exciting. And also there's a lot of talk of missions to Europa, which is also very exciting. So, if we were trying to understand life in the universe, I think the first step is understanding life in our solar system. Probably also life on Earth, which we understand quite well, but really not that well.
Right.
There's a lot about life on Earth that we don't understand. I think.
Correct me if I'm wrong, but the best understanding of, we seem to understand it in an outline, right? There was like a concoction of chemicals in in an ocean at some point, triggered formation of life. I feel like that's our explanation of it. It's not very detail heavy.
Oh yeah, no, right. We don't know how life formed on Earth, right? We don't. But we kind of have a vague idea of how life can form, right? It's just like some chemical process formed life. But even the life that exists on Earth, I don't think we understand super well. That exists right now.
Right.
What kinds of life are possible? I think we don't really understand. I mean, probably biologists are gonna shout at me for saying this. They definitely know better. That's their field. But I think life is still surprises us sometimes. It's we find it in places that we don't expect, and I think that's a sign that maybe we need to understand life on Earth and life in our solar system, if there is any other life in our solar system, before we can really start thinking about what life outside of our solar system looks like. Even though, realistically, it should look similar, because the reason that life looks the way it is, it does not. I don't mean on a people and trees sense, but a chemical in a chemical sense, is because of the way chemistry works, right? Life, the chemistry of life is dictated by the laws of chemistry.
And carbon is just, you know, a good way to make life. It's like carbon is just like the most has the most complex chemistry of any other element, and that's why, like, complex and stable, like, surprisingly so. Like, it's amazing to me. It's amazing, like, the things that carbon can make. All of, and that's I think why life is carbon based, because carbon is common, and it also has very interesting chemistry, and it allows for complex things to form.
Fair. And I think my last question before we close is, based on, you know, what you know about formation of stars and planets, what do you think is going to happen to Earth and our solar system? In, you know, what's the, like, the time frame, and what's the event?
Right. Well, that's a hard question. On, like, there's like many time scales, like many orders of magnitude, right? In the short term, I mean, if you think about what's it called, Bayesian probability, we expect we expect civilization to be around more or less as long as it has already been around, right?
That's it?
Well, usually the best guess is, like, if something's been around for a certain amount of time, right? The most likely thing is that you're in the middle of that time, not at the very start or at the very end.
Mm-hmm.
Just because it's unlikely for you to be at a very important specific time. So, you know, most likely you're somewhere in the middle of how long civilization will exist for. Of course, it's a contentious way to think about it, but, you know, most likely, you know, we expect civilization to probably be around at least as long as it's already been around. It'd be surprising if we were around at the end of civilization. If we don't do something, global warming will make the Earth look quite different than it looks now, but not different than it's ever looked. You know, the Earth has before had a huge amount of carbon dioxide in the atmosphere. There have been periods in the Earth's history when the South Pole was a moderate, like a temperate rainforest kind of environment. And, you know, I guess we are pushing the Earth back into that direction, which is a terrifying thought, of course, but it wouldn't be, you know, it wouldn't be a crazy change for Earth. Life will probably survive. Humanity, maybe not, probably not, but life will probably survive. Then after that, what's going to happen is we possibly have a lot more certainty of what's going to happen after. Over the next 5 billion years, more or less, the sun is going to get hotter, grow, turn into a red giant. It will most likely grow to encompass Earth. Like, the sun will probably be as large as Earth's orbit, so Earth will probably not survive, or if it does, like, it will be very stripped. Like, the surface of Earth will be very stripped. I mean, that's the end of the Earth, and then the sun will blow off its outer layers and be left as a white dwarf, and the rest of the universe will be none the wiser. Of course, eventually, at some point, the universe will cease to, well, exist in the way that we know as well, but that's a very long time down the line.
Wait, because the universe, they are dating it for around 12, 13 billion years?
13 point something billion years.
Right,
yes.
So one would say that 5 billion years is actually pretty long time scale for the universe, and so the stars are pretty. Are they kind of like important building blocks of the universe? Because from what you're saying, they've been around for quite. They must be around for quite long, or it actually depends on the star.
Well, it depends on the stars.
Oh, okay.
So the very first stars formed only a few 100 million years after the universe formed. I think it's a few 100 million years. I'm not entirely sure. But yeah, I think it's something around along those lines. Maybe 1 billion years after the universe formed, but I think less than that. And some stars are extremely old. Like, the thing is that a star's life cycle is dictated pretty much entirely by its mass. Very big stars burn extremely bright. The fusion in their cores is very fast because there's like a lot of gravity, a lot of pressure, and these stars, like they only live a few 100 million years, a billion years, and then they spectacularly blow out. Right? You get they're small enough, will blow out, will explode in a supernova and leave behind a black hole or a neutron star. If they're even larger, they'll explode in spectacular supernova explosions, and leaving behind not even a black hole. The explosion's too violent for the cores to collapse into a black hole. It's kind of crazy. I don't know how it works, but
so the standard pattern is for a star to explode into a supernova and create a black hole?
Well, yeah, pretty much. Like for larger stars, for what is called.
Is our sun a large star?
No.
Oh, okay.
Our sun is a medium-sized star.
That's why it's not gonna explode into a supernova and turn into a black hole.
And that's why it's a black hole or a neutron star, depending on the size of the star.
How are the two different?
A neutron star is just not quite massive enough to be a black hole. So when fusion inside a star ends, there's nothing to balance out the gravity anymore. So the core starts to collapse, and depending on the mass. For our sun, what's gonna happen is like fusion ends, and then everything collapses. And the thing is, physics doesn't like two electrons to be in the same place at the same time. So that causes like some inherent pressure, and everything's going to collapse up to the point that the electrons stop it from collapsing, right? Because they're pushing away from each other. And so our sun is going to collapse up to that point, and then stop, because there isn't enough mass for it to collapse further. In other cases, there's much more mass, and the electrons will will get pushed into the nucleus of the atoms, and the nuclei themselves will collapse into just neutrons, because you can pack neutrons more closely together, and that's how you form a neutron star.
Okay.
Of course, if they're even more massive, even the pressure of the neutrons pushing against each other will not be enough to stop the star from collapsing, and that's when you get a black hole. You just collapse, you keep on collapsing, and
Got it.
you become a singularity, right? That's the idea of what happens, and you get an event horizon and all of that fun stuff. That's not going to happen to our sun, because our sun is not very big in the grand scheme of things, and that's the thing, right? Like, our sun is going to grow into a red giant at some point and blow off its envelope and become a white dwarf, which is like it's like just the core that's left over, and it's extremely hot because there was fusion going on there, and it was the core of the sun, so it glows extremely bright. That's why it's white, and eventually it will cool off over billions of years. But the thing is, like, the larger a star is, the less its life cycle is. Very large stars will, within 100 million years, will have gone through their whole life and explode into supernova. Medium-sized stars like our sun, they have lifetimes. You can expect them to live up to 10 billion years. Like, our sun has been around, I think, already like about 4 billion years, 5 even, and it will probably live about as long as it's already lived. Very long amount of time. Red dwarfs, which are even smaller stars, they can survive tens of billions of years. I think we have observed red dwarf stars that are nearly as old as the universe itself. They've just been around forever. Well, forever. It's a big term, but I think the oldest one we've observed is more or less 10 billion years old. Right, so it's predates a lot of like predates pretty much everything we see in the universe. You know, it was there. It formed like along with like the galaxies forming and stuff. It's kind of crazy.
What's the reason for the decompression of sun after the nuclear fusion in its core runs out? Why does it turn into this red giant that you were talking about?
So what happens is that currently the sun is in what is called the main cycle, and the energy is produced by like different fusion processes. A lot of them involving hydrogen. After you're done with all the hydrogen, then fusion kind of stops and the core collapses, and that heats it up a lot, allowing for different fusion processes to take place. So you can start fusing things into carbon instead of helium, and that produces a lot more heat, right? Produces a new wave of heat that like expands the outer layers, and if the star is massive enough, once that stops as well, then you get further and further fusion until you get iron. Iron is the point at which fusion is no longer energy. It no longer outputs energy. You know, if you fuse 2 iron nucleons, you don't get any energy out. And at that point, fusion stops, right? Because you're not getting any energy out. And yeah, maybe you might be fusing some iron nuclei because of the temperature and the pressure, but you're not releasing any more energy to balance out gravity. And at that point, the star collapses and you get a supernova. Supernova is kind of crazy, right? Because it's not... Stars are like constantly exploding balls of gas, right? But like gravity holds them together. What happens in a supernova is that the ball of gas stops exploding and like supporting itself, so the outer layers just like kind of fall in and they bounce, and that's the explosion. It's like everything collapsing in very fast and like causing huge amounts of heat and like unimaginable amounts of heat, and that blows off the outer layers.
But because sun is not big enough, that's not gonna happen.
Exactly.
Okay. So essentially it's gonna expand because it's not gonna be one rapid explosion where it throws everything around. It's
the fusion is gonna stop more gradually, and it's not gonna reach iron.
So the essential reason for that is the gravity will stop holding sun together, and that's like the density of sun will get less. That's why it's going to become bigger, or
no, it's just the heat is going to increase in the core, produced by the core, which is going to blow it, like make it larger, turn it into a red giant, and then as time goes on, the outer layers of the red giant get blown away by like all the X-rays and like, stuff produced in the core.
Got it.
And it forms like a nebula.
Mm-hmm.
I think like the Crab Nebula was formed by supernova, I think. But like there's nebula in space that you can observe with telescopes that were formed by like red giants blowing off their outer layers, and it's not like super exciting, it just like gradually blows off all the outer layers. The stellar winds blow off the outer layers, and you're left with like a hot, dense core, which is just it's tiny. It doesn't have the mass to do anything interesting anymore, but it's still extremely hot just because of all the fusion that was going on. Nothing's going on anymore. It's like a huge ball of carbon, usually, mainly carbon, and it's just super hot, and it's emitting a bunch of X-rays and a bunch of light, but it's really tiny, so it's not enough to heat anything, really.
Wait, I'm just dying to ask this last question. Is there some sort of astral recycling going on after that? What's gonna go? Because...
Well, I think it's Carl Sagan who would say this, and it's like we are all made of star stuff, and that's kind of true, because everything that we see, like all of the bigger atoms that we see were formed in dying stars. The fusion in dying stars is what formed carbon and all the heavier elements that we see. Even more interesting, quite recently discovered that a lot of the even heavier elements, so like gold and uranium, was not even formed in supernova, but rather was formed in what's called a kilonova, which is the collision between two neutron stars.
Whoa.
And we observed the very first one, was it a couple of years ago, using the LIGO observatory, which like observes gravitational waves, and then we saw the signature of two neutron stars merging, and then we also saw that with the telescope. Kind of crazy that like we can do that. But yeah, so all of the things we see, all the dust in space, is formed in stars, and then when stars die, they blow it off, and then it gets incorporated into the next generation of stars and forms planets and all of that stuff.
Okay, I see how. Okay, that makes perfect sense. Okay, I think this is gonna be. We're gonna call it a day.
Yeah, sure.
I want to thank you very much for
no problem
explaining all this wonderful and amazing stuff. I think I feel a little bit less ignorant now than I felt an hour ago, thanks to you.
Oh. I don't know. I think most of the time it's just a chat, right?
Exactly.
Thank you. A lot of the stuff I don't know either. So.
Yeah, no, but thank you very much, and see you soon to those who listen to this amazing podcast.
Bye-bye.
Thanks.